All right, so this is my last lecture series for today, or I guess for this entire camp. It's gonna be a little more high level, a little more entertaining, I hope, compared to the earlier lectures. And it's gonna be about my ongoing research, some of the few recent ones and also some of the new ones I'm working on right now, okay? So the title is Visual Cognition for Interaction, and the name says all at this point. So let's start the talk here. Okay, so, oops. Oh, I didn't put this, sorry. Yeah, give me 1 second. All right. Okay, I don't know how many of you have seen this video before, but this is the robot built by Boston Dynamics, which can do a lot of, human actions. You can sit, it can jump, it can stabilize, it can even do bed rocking and all that too, right? It's not trained by machine. It's just it's basically engineered by humans, but you can see it can make a lot of very stable movements, just like a human. So probably better than actually me. I cannot do back jumping like that. And now in computer vision, I already showed this video earlier, but we have a very reliable object detection or human pose estimation or all the other problem-solving algorithms now. And some of it is actually even better than humans or faster than humans at least too. So the main question we can ask is, are we ready to build an AI robot? We have a very reliable computer vision system, and we have a very reliable mechanical system for a certain extent. And is it good enough to build a AI robot? I don't know how many of you, did any one of you actually come to my talk last year? I know a few, but hopefully not too many, because it's gonna be, there are a lot of repetitive part here. Okay, so let's take a look at this rectangle here, which is apple. How many of you want to eat this apple? Or how many of you not want to eat this apple? Anyone who want to eat this apple? No one? Okay, who doesn't want to eat this apple? Oh, okay, you guys are pretty good at guessing. Okay, all right, yes. All right, there's a person here. What is this person doing? Can anyone tell me what this guy is doing? Right, I mean, the bounding box was not enough, right? This person is skydiving at this point. So what I want to mention, the point I want to come across in these two slides are that bounding box detections or even semantic segmentations are not enough for us to interact with the scene. Even though we have a very reliable bounding box system or detection systems or semantic label, right? That's not enough. So here, let's see a picture here. We see this image of full interactions of humans and also environments. And we can also find all these bounding boxes or pixel mask and whatever at 100% accuracy even, let's say. But at the end of the day, this is what we train machines to see right now based on these detection systems, right? And how many of you actually can tell if this grill is gonna fall down or if this person is happy or should I actually eat this meat? And we cannot answer any of this question right now, right? So to answer this question, or answering this question essentially is part of my ongoing research topics. So we have robotics and computer, which was actually started from one same field at least several decades ago, but they have been segregated quite a lot because they independently it was its own hard problem. But as we are starting to solve or have a closer to be solving many problems, their gap is starting to get reduced. And my goal is to solve this cognition problem that resides between robotics and computer vision, okay? And this means, for example, understanding physics, being able to plan things, as well as guessing what the affordances of the objects, and being able to assemble the furnitures, and answering questions, and navigating the world as well, right? And so to address all this issue, we need a good learning algorithm for vision and combining vision and robotics altogether. And that's what I call by visual cognition for interaction. Okay. So how do we start? Where do we start from this? Okay. It's a hard problem, and many of my research topics has tried to get some inspiration, not direct inspiration, but try to be motivated or get inspired from how humans or human babies learn, right? So obviously we don't learn from direct supervision every time, right? We are not told what to do every single second, right? From our parents or our peers, right? We observe things, right? We sometimes just simply observe the world and learn from it. And sometimes we interact with it and we get a feedback and learn from it. And sometimes we ask questions, and sometimes we also learn over time. It's not a single shot learning all the time. We accumulate our knowledge over time. We inherit some of the genes from our ancestors too, right? So my research is about basically learning through observation, interaction, question, and lifelong learning for interaction, okay? And let's first talk about learning through observation. And for learning through observation, one of the key topics I addressed is understanding physics around the world, right? For example, the physics, why do we care about physics? Because physics is important, for example, for us to tell whether this grill is stable, right? It's an important question for our safety, right? If it's gonna fall down, we wanna make sure you will stay away from it. And that kind of answering that kind of question is about understanding physics, and that's some of my research project try to address this issue. And physics is not only about grill, obviously, right? We try to understand, interpret the physics around us everywhere. For example, if you want to balance this bicycle so that you don't fall down, right? You don't trip down. Or if you want to hammer the nail into the wall, also you need to know how much force you want to apply so you don't by mistake you don't hammer your hand, or you don't hit too lightly so it doesn't do any interaction, right? So the understanding all this is understanding all this, or being able to act around the world, require understanding physics. So this is a very challenging problem which not too many people addressed in before. So we try in our projects we try to simplify the world as much as possible, and in a more lab environment. And let me show some example here. So here I'm showing I'm going to show you a video, okay? And the question is, where will this green box end up reaching? Okay? So let me show you a video. I'm only showing halfway right now. Right? Okay? This is so it will there's more video going. So let's see. Where do you think this green box will go? How many of you think it's A? B? Okay. And C? Right, okay. So that's good. No one said it's A, right? We know based on our experience, the chance of this green box goes to A is very low, right? And I think the actual answer is a C in this case. But the point was no one guessed it's A here, right? And why is that actually? How do we know this? And what's going on in our physical world here? In the reality, what happening behind the scene is actually the object has certain density, friction, and volume. And another object has another density and friction and volume. And we also see certain inclined surface here, right, at the bottom. We see some degree, it's actually inclined surface. And which means the density, friction, volume actually constrain what the mass and velocity is, right? And then there's a kinetic energy and momentum in the physical world, and they're interacting to each other and eventually create the video we watched, right? So my project was about basically developing a model that can predict this is such a physical properties and outcomes based on this understanding this physical rules. But one key component, one key contribution was we don't use any explicit annotated labels. So we just learn from observation rather than having to label all the object labels, right? So for example, if we're just doing deep learning 101, what can we do? We just label this density of this object, friction of this object, and volume of this object, and we just train a AlexNet or whatever architecture, right? That's one way to go, and that's probably the simplest thing to do. But obviously, we try to avoid. Our goal is to always trying to avoid this explicit supervision or annotation, right? And that wasn't one of the motivation. And by using physical constraint. For example, humans never have to learn like how heavy it is, how light it is, or how big it is, and so on. But we can just by watching the world or interacting with it, we can already interpret and what will likely happen and so on. And that's kind of the motivation here. Okay. So the high level approach for this is very simple. just like I said, it's a physicist worked really hard, essentially, back in the day, to figure out all these physical laws, right? F equals ma, all the kinetic energy rules, and we just all we had to do was just encoding all this rule into the network, okay? And let's take a look what I mean by this a little more carefully. So here's an object here, right? Just I cropped the image of this object, which is surrounded by the external world, right? So if you think about it, this object has a certain material, right? And also has a certain volume, right? And the materials defines the density, right? And the material also defines what the friction coefficient has to be. And we know the mass is density times volume, right? This is from high school physics. And then friction is basically constrained by mass and friction coefficient also too. I can go on and on and on, and then talk about all the physical equations. And then finally, with interaction with the external world, we get to we will reach the physical outcome here, right? And that's what we observe. So that's basically what produced this kind of rule is what produced this video output we watched. Okay. So now let's step back. How can we utilize this? So here's the object, right? And let's just suppose our goal is to train a network that can predict the volume, right? So let's suppose this is our target. Our target is to predict the volume of this object in the image. Okay. And again, if this is if we can just utilize all the labels and annotations, we can just train some simple network with the label of this image and the volume, another image with another volume, and then we can train a network simply doing that. But that's not desirable, right? So now the question is, how do we do this without direct annotations? And the interesting part is this target is latent, right? We cannot directly observe it because we don't have a label for them. But there is something we can observe directly from the video. For example, velocity. The velocity is already freely given in the video. We don't have to have labels, right? When you see an object moving, we know the speed, right? But based on the physics rules I talked about earlier, right? The volume and the velocity is all connected. It's not independent variables. What I mean by that is it's all connected through this type of physical equations and constraints, right? So simply what we mean is we have a latent variable, volume, which can be supervised by velocity, which is observable. And the loss function and all this supervision will be coming out of trying to constrain this velocity, which is given from the video. And then it's basically going to all go down all the way to volume here. And I will talk about a little more in details as a model architecture, okay? And that's the same thing for material. If our goal is to predict the material, rather than directly supervising or computing loss function of the material here, we have observable variable here, and which can be velocity, and it can be other variables too. And based on these observable variables, we go all the way down to material. Okay. So putting it short, rather than trying to supervise or putting the loss function of volume or material directly, because we don't have a label, we go up and up of the physical trees, and go to the whatever is observable, and put a loss function or supervision on this velocity variable. Okay. So it's kind of connected to what's called distal learning, where we have something. Our target is to predict certain things, but which is unmeasurable. We don't have a label for, but we have certain outcomes which is directly measurable, and then we supervise them directly. And if we put in a more of a familiar deep learning architecture here, at the bottom we have videos. And using some simple tracking algorithm, we extract all these image patches here, just like object image I showed earlier, right? The doll here. And once we have this image patch, we have convnet connecting to material, and another convnet connecting to volume, right? So again, if we are doing simple deep learning stuff, we can just put a loss function onto this volume based on this ground truth label of the volume and predicted outcome. And we try to reduce this gap of this convnet predictor. right? Whereas but we don't have a label. So what do? So we connect this volume, so predicted value, and material connected value, predicted value, and then go to density, connected density layer, what we believe is density layer, and then we connect this to density layer and volume layer to mass. And we know this can be hard constrained. So when we have density and volume, we can simply multiply them, and that will create a mass layer, and so on and so. And we'll go all the way to velocity and displacement. I'm skipping some details, obviously. There are some more intermediate layers here, too. So the nice thing in this case is when we go all the way down up to the velocity layer, we have ground truth label, which is coming out of videos freely, right? We have ground truth speed of the video. And then we have a predicted speed of the velocity based on these layer connections. And we compute a loss function, and we can supervise them. And we have displacement, and we have other variables, too, like a sinking speed or bouncing height. When you drop the ball, you can see how much it bounced and so on. And by constraining every possible different observations, we can self-supervise them. So once you have supervision loss up here, these upper layers, by just simply doing backpropagation, all these supervision signals will go down all the way to even these lower layers, and then we end up getting this confidence to be able to predict volume and material. Even the only thing we constrain is or supervise is these upper layers, but which the labels are coming for free. Okay. Yes.
I assume that you were using then the laws of physics in order to connect the
That's right.
mass and
Exactly.
material.
Yes, exactly. Yep. So we have all these connections in between layers to layer. If we have certain physics rules we know, we constrain it that way. So basically, again, mass is density times volume, and kinetic energy, one half K mv squared and so on, right? That's basically what we strictly encode. And some layers are just freely connected. For example, material to density, there's no physics rule connecting it. It's just once we know the material, we know the density kind of thing. So that's how we constrain it. Okay. So that's a simple idea was used to self-supervise all this physical property predictor. And again, the emphasis was on not having any ground truth label and learning from just a pure observation. And we call this as inverse physics because going upward is following the typical physics rules, and we are inverting the physics physical directions, and to train everything in between. Okay, and we can connect all the higher layers, and eventually within our network, we show this kind of video many times with 10-20,000 videos for different type of objects here as well. You can see we try to vary the size of the objects or shape of the objects or color of the objects or even the material and so on. And sometimes we try to have same shape but with a different material and so on. And then we train our networks with these videos. And once we train this network, we can try on this video, right? So here we are showing the very first frame, and our goal is to be able to predict what will likely happen. Okay, just like the test I did. When in your test, I just showed the first half of the video, but in this now we just need only first frame, to predict all the material and volume and all that, and then compute all this forward engine. So at the bottom, we show the predicted outcome of our method, right? So this is what's likely going to happen or predicted to be happening, and actual result, you can see it's roughly correct. There's a little bit of rotation here. Other than that, it's the speed and all this result seems quite reasonable. And it's not just about falling, like slope on the falling on the slope, sliding on the slope. And there are other scenarios like springing or bouncing in liquid, like floating on the liquid. And we tested all these scenarios all together. And we also compare against humans. So we show some examples to humans, like I showed to you. So we show some training examples to humans, and we tested them too. So if you look at this, this white cross here is where the actual outcome was, so where it actually stopped. And then the orange cross is where the model predicted to end. And then this heat map is where we asked multiple people. So multiple people predicted. The heat map shows how many people predicted that kind of location, right? So on the left side, you can see it's humans and machines are all more or less reliable. And on the right side, you can see while our model predicted reasonably, some humans have gross errors too. It's non-trivial problem actually to humans too. Okay. So this was our first project related to learning through observation to develop a model that can predict these physical outcomes and properties as well. Is there any question about this work? Yes. Yeah.
How many videos did we train?
So how many videos do we needed to train? So we trained with about 20,000 videos. So when I said 20,000, it's basically all these objects times 2, because we have very target as well, times 4 different viewpoints. Yeah. And we also have multiple attempts per object, per scenario. So I think about 3 or 5, I don't remember exactly. It's a little old work now. So yeah, the hardest part was creating this video. I was a postdoc at then, and then one of my PhD students and me took all this video. So we had to spend several weeks to collect all this video ourselves. So if you look at this video, in this case, this is my student's hand. And also I have other video, which is my hand, and so on. So you can tell. It was a very hard work from that part. Okay. Any other question? This is what you do when you do PhD. Keep sliding objects. So be careful. Okay. So if you don't have it, yeah, go ahead.
And I see you use the human hand to release the object.
Mm-hmm.
Why did you use the machine to release? You can control the angle and
I see. Yes, that's in some sense, very good question. One, we couldn't find the right tool for that, I guess. And 2 was just more convenience, I guess. But in theory, yes, you should probably use more accurate tool to do it.
And you can collect more video by using the machine.
Yeah, but the problem is you have to have a machine to bring the tool to the, you need a tool to bring a fold object to the machine, and you have to keep doing this too, right? I mean, yeah, in theory, if this was a really big project, then probably we can even build our own tool to make all automatic process. But with a 2 PhD student in computer science, we didn't have sufficient knowledge to the mechanical engineering, I guess. Yeah.
So actually,
Yes.
some hidden variables in your model, right? So for example, like the mass and so on.
Yes.
And try to verify the.
Yes. Yes. So I'm assuming your question was, so there are all these intermediate variables too.
Yes.
And did we check how accurate they are?
Yes.
Like how accurate is mass, for example?
Yeah.
Yes. So in the paper we evaluate. So it's not just that we do qualitative result. Actually, I had a plot. I don't know why I removed it, but we evaluate how accurate our all this prediction is compared to actual ground truths. Yeah. For example, how good is the mass compared to ground truths? How good is the volume compared to the ground truths, and so on. Yeah. And we also validate it based on how many examples do we show, how many near a family of classes too. Like, if we show more closer objects to target, then they predict better. Like, for example, suppose that I trained everything but this object, then obviously it's the easiest, right? So if I have so suppose this is target object right now. So let's suppose I remove this. And if I train using all the other videos, then the prediction usually is more accurate. And if sometimes what we did, we removed all this family of the objects here, and then train with everything else, and try to test on this object, then that accuracy goes down, obviously, too. Yeah. So we have all this variation of plots. Oh, yes.
Back to the architecture of the network.
Yeah.
Yeah, and my question is how to constrain the node to be volume or mass.
So how do we constrain this to be volume?
Yeah.
So this is abstract concept, right? We just put a layer here, and by connecting all this and follow the physical rules, the only thing that can be reasonable to answer this layer end up having to become volume. Otherwise, it cannot make a sense of every other connections. So it's overly constraining it. That's my answer.
Then does the node finally become the volume?
Right. Yeah. Exactly.
Do it,
Except the normalization factor. There's one other thing I skipped, which is a normalization factor. So you have to normalize it to compare. Yeah. Wow, you guys become more active after lunch.
So when you were using the doll,
Right.
then depending on the direction or orientation of the doll, you had very different properties.
Yes.
How good was your model at predicting that?
Right. That's also a very good question. So we make an assumption that it will only roll. I mean, we don't make any roll. So we always try to make a sliding movement without any rolling, and only through one direction of the objects. So suppose in one video, if the doll we slide it in toward using the head, then we always slide it with the head. So we don't do flipping, for example, or rolling, for example.
Okay.
Yeah. So we follow a very simple physical world rule, I guess.
I think that was a pity because that would actually have been one of the cases where I think your model could have outperformed what people can do with physical models
that's
if
also
you would
true.
have combined those two.
That's right. Exactly. I guess the hard part was just putting everything into this network with all this complex physical engine or physical rules was a little tricky, and that's why we avoided it in this case. Yeah. Yes. I guess that will be my last question for this part.
Hi.
Yeah.
Did you find anything interesting when you compare the weights you trained to the real-world physics law?
Oh, can you speak louder?
Did you find anything interesting when you compare the weights you trained out between the real-world physics law? Does they actually obey?
I don't think I understood the question. So did I find anything interesting when I
Yes.
trained?
Based on this network, and when you check the weights, do
Right.
they actually obey the real-world
The
physics?
weights, you mean the parameters of the network?
Yes.
But the parameters network is not directly interpretable in this case because the rule is encoded into the architecture. The rule is not encoded into the parameters. We already encode every rule into the network itself. So the weight is not really directly interpretable per se. Yeah. Okay. All right. So that's one of the first work. All right. So the second part is imitation learning with GAN. I know the GAN will be discussed a little further tomorrow. Have you guys played with the GAN or know anything about GAN? Or not know about anything about GAN? Again, you guys become inactive. So I should not ask whether you know or not, I guess. All right, so I will assume you guys all know about GAN then. So anyway, so the GAN is a very popular technique, I think, which will be much further discussed tomorrow by Alex. But our work was, so the GAN typically has been used to generate interesting images or like art piece works or facial expression and things like that. And I think that will be discussed further tomorrow. But we applied this GAN models to do imitation learning. And what does imitation learning mean? So imitation learning is, as the name says, so humans have this incredible ability to follow others, right? We can imitate them very well, right? Here you can see the baby. Without knowing what he is doing, he can just try to mimic and imitate other people's actions here. And that's what we want the machines to be able to do. So for example, when humans do some actions, we want the robots or agent to follow and imitate human actions too. Okay? So let's take a look at, with that in mind, let's take a look at this video. Okay? So here I'm showing a walking pole, right? So that's one way to walk forward, right? And there's another way of walking forward as well. It's a different style, as you can see. It's both are walking, right? They both walk well, but it's just a different style and different speed and so on. And there's another way also, again, to walk forward too. Again, it's also walking, but in a different style, right? So I showed 3 different styles of walking forward. And it's not just that there is only walking forward. You can also walk backward as well, or move backward, essentially. And as well as jumping as well. So you can think about all different types of movements and different styles of each movement type, right? So in other words, we have this table, right? On the y-axis is a different style. X-axis is about different types. So this axis shows different styles of moving forward. On the upper, this x-axis shows different types of movements. Moving forward, moving backward, and jumping. So let's suppose this is like a demonstration. So this is let's suppose what we want to imitate from, right? We want a machine that can imitate from these actions, right? But what's it like? What's in the world? In the real world, we don't have labels, right? We don't actually have label like, okay, this is a style 1, style 2, or style 3. We don't also have a label like, oh, this is moving forward, moving backward, or jumping, right? If you imagine like humans, let's just pretend this is like a human actions. But we don't have labels, so we just see them, right? We just watch how humans move around, and we try to mimic it. That's how babies do, right? When babies learn to walk, we don't tell them, oh, this is a movement A and that's a movement B, or this is style A or style B. We don't say that such thing. Just baby watch things and they learn. And that's also true. That's basically what the real world scenario is without label. Yes?
So I would just like to comment that when it comes to babies learning to walk, it's not really that simple, because it has actually been shown in studies that we have a special neural circuit in our spinal cord which generates the basic pattern for walking. And what the baby basically needs to learn is just how to modify that pattern so that it stays balanced.
Yes.
So it's evolutionary, actually, the basic pattern is programmed into us.
I see. Yes, I was afraid of having such audience in the crowd. Yes, it's true. So I mean, walking in this case is just exemplary point. Yes, it's true that in the actual human walking, we don't learn in such a way. But I just wanted to show this as an example of, examples, I guess, rather than a real scientific meaning in it. Okay. So what I mean by this is we have a lot of demonstration from the world, but we can just mimic it without actually having labels. And that's also what we want to achieve in a machine setup as well. So we have a lot of labels, right? But without label, just random demonstrations. Just like, again, babies can learn from this unorganized set of demonstrations, right? And as, for example, if we have this type of different type of movements, running forward and backward and jumping, we can just learn from them, even if we don't have any labels. And how do we achieve it is basically going back to GAN. So again, I'm not sure how many of you are really familiar with the GAN right now, but GAN at a high level is very simple. The entire goal of GAN is, the goal is to generate sample, which is X in this case. The goal is to generate X image, generating images as close to the real images. So as long as you can generate some images that look like real images, this loss function is very happy. Okay? That's all you have to understand for today in this lecture. Okay? So the goal is to have a loss. So the GAN is all about having this loss function, which is about generating. When it's happy when the generated sample look like real samples. And samples mean, in this case, images. For example, X. Okay? And in GAN, there is something called InfoGAN, which now as this extra term. Oh, forget about what I said. Okay, so that's basically what GAN is. Okay, and then what we do in the imitation learning setup is this. So we, instead of having X, which is generally image, we now replace to state and action pair. So S and A, right? We saw this a lot in the reinforced learning setup. So all we care is this generating state and action pair that looks like a real state and action pair. Okay? Does it make sense? That's all we do. At least this is actually one of the work doing this. So we have a lot of demonstrations which have a state and action pair. Okay? And our goal is to generate some random samples that look like this state and action pair we saw from the previous training data. Okay? Just like this earlier. So in typical GAN, it's about generating images that look like real images. And in our case, it's about generating some actions that look like real actions. Okay? So that's what it was. But the problem, there's an issue here. Because in this setup, we don't have any interpretability. So we cannot control what action it creates. So we don't know whether it's moving forward. We don't know whether it's actually style X or Y at all. Like, there's a different styles, or whether it's moving forward or backward. There's no control of this issue. So when we have this kind of demonstrated data, oh yes, go ahead.
So you are the SNA sample
From the generator.
It's not sample from noise.
It's a sample from noise to generate a state and action pair, yes.
So it's
Yeah, the generators generate state and action pair from the noise, yes. Okay. This part you don't have to understand if you're not familiar with GAN, okay? Yes. So with this, so what that means, so when I say no interpretability, let's go into this demonstration data. So we have lots of these demonstrations, okay? Lots of videos. They're actually supposed to be video. And then once we train this generator, the generator that generates state and action pair that looks like a real data, then the result will look like this. So you can see it generated something that can at least walk. So if you don't have this, you cannot even expect it to walk. It will just immediately fall down or just kick the leg, for example, without walking. But all it can generate is just this one sample. Pretty much that looks, almost everything looks like this. They have subtle difference, but they almost look like exactly this. Okay. Technically it's called mode clasping in GAN, but which just means it can generate only one type of samples. Mode means that in this case. Okay. But one thing we know that there's like a different style and type, and how do we actually create this kind of variations, and how do we control this variation was a key question here. And for those who are familiar with the GAN video lectures, there's some already work trying to do this in image generation, which is what called as InfoGAN, where they try to not only to so the standard GAN, the standard classic GAN was to generate any digit images. As long as it looks like a digit, it's happy. It doesn't have to look different even. It's as long as it looks like a real digit, it's fine. But the InfoGAN introduces some extra term to control that it can vary the thickness, and also it can vary the digit type here, like what digit it generates. You can see as it moves to the right, it looks like a thicker digit, and also you can see different digits it produces too. So the InfoGAN interests how to control this essentially. Okay, one way to control this, and that's the contribution of this InfoGAN earlier. And we basically adapt this as well into our framework. So from this framework, we introduced this interpreted term, InfoGAN term, information loss term, in the blue box, just following the InfoGAN, okay? And with this, we also have this interpretability of stated action pairs too. So now finally with training this, with training data, again, I showed you this imitation GAN we call, without information loss, just can produce this kind of result. And again, we cannot even control anything. But now with information loss introduced, we can have an agent that can move forward and now also move backward and also jump as well. And we can also control this too, meaning we can generate sample we want of, like if we want intention 0, meaning style or type 0, it can generate moving forward or moving backward or jumping and so on. All right, and it's not just about this pulse. There are more examples. So same thing, like a little more like humanoid ones, and again, imitation GAN without information loss has this, again, mode clasping issue as well as no interpretability. But now with information loss, we can generate more samples. And we can vary the style as well, too. And there are more and more examples on our paper on the website, too, if you're interested. It's not just about walking or moving. There are also grasping and other kind of more different type of tasks to begin with. Okay. All right. Is there any question about this work? No?
But I suppose in
Yes.
every, so now I suppose in different categories of movement, you still have the more plus problem.
Different category? What?
For example, now at a side, now you should walk
Right.
forward, but for the samples that you generate by condition on a specific moving forward action, you still have the more plus problem somehow.
Oh, no, we don't have mode. I mean, okay, mode clasping was not it wasn't our intention to solve mode clasping issue, actually. But apparently by introducing this information loss, it also solved mode clasping issue. Well, at least in some sense, at least it looks like visually, all the mode clasping issue has been gone. But it was not our intention. Our intention was actually really to control this, whatever it can generate, so that we cluster them into one cluster. But apparently, it also has resolved this mode clasping issue. It was more of a side artifact, which is good result, but at least we don't know why that exactly happened. So, yeah. In fact, we were thinking about looking into this a little more theoretically, like why this information loss resolve any mode clasping issue. But we didn't look into that more in details. Yeah. Yes.
I don't think actually solve the mode collapsing. I think you are limit some acceptable mode for the in this imitation.
No, it's true that it's potentially could be there more. It's at least it's okay. It's a technical. It's hard to argue because it's all qualitative at this point. But before it was a completely one mode. At least visually, it looked like a one mode there. And then when you added this information loss, at least it was more than enough modes that we cannot visually say how many modes are there. So I'm only showing 3 demonstrations, even within each intention. So suppose meaning even within walking, there are more than one walking styles we saw, and they are all a lot. They look visually very different at least. But maybe if we count, maybe there are a certain number of modes. But we never really tried to count it, but definitely it was more than just 3. Even though there are only 3 types of intentions, but there were definitely more than 3 modes, like by probably at least a few factors. But we don't know what exactly happened, okay? Okay, any other question? All right, okay. So, and then now we can move to the next project again. But if you have any question, please let me know, okay? I don't know if I'm going too fast or slow. So the next project was about learning object functions or affordability from videos. And then we define a specific way what we mean by affordance in this case. Okay, and this work was done with Quan Fang and Dalin Wu. I mentioned this specifically because Dalin is, oh yeah, actually this, I thought you guys are all from NTHU, but never mind. So anyway, but now we are at NTHU. The student is from NTHU, but I guess maybe not as relevant to everyone here. Okay. Anyway, so what do we mean by this? So when we see this object here, okay, how many of you actually know how to use this tool? I mean, really, is there any one student who knows how to use this tool or know what this tool is? At least I didn't know. I cannot tell. I still don't know the answer exactly yet. Okay, so no one, let's say. Okay, so no one knows, right? So now let's suppose I give this to you, really, like physically. How will you use it? Where will you use it? Or how will you figure out how to use this? Try everything out. Yeah, trying everything out. Oh, yes.
Well, I would start by trying to use it to fix my bike because that's what I would guess it is for.
I see.
based on what parts you can see here.
Yeah, but I have no idea either about how to exactly use it. But as he said, the first thing to try is just trying to guess by inspection, right? So it looks like it's like a kind of keychain kind of look like, and there's something definitely saying rotate, so maybe it's something to rotate around. And it looks like there's a sharp part, which looks like it may be cutting something, I don't know. Like I'm just randomly guessing myself too, right? So one way to figure out how to use this tool is by inspection, right? And the other way of doing it is, as she said, is by trying out all these random things, right? Like you can just randomly push it or throw it or whatever, and then you can start to realize. But then the problem with trying out is not only is it hard to figure out, but there are cases you may not want to just try random things out, right? I mean, the base will, obviously break, and you probably don't want to touch this sharp part because, I mean, suppose you don't know anything about it, you may just touch it, and obviously you don't want that to happen, right? So based on this, our goal was to learn this affordance, basically how to use this tool by watching other people's demonstrations, right? If we see other people using it, then it becomes much more clear, at least to many of us, how to use this tool, which means learning affordances from demonstration. And that was basically our high-level motivation of this work. And how we do this is we just collect a lot of demonstration videos from online, from YouTube, okay? And ultimately, the key contribution was to collect this data, but at the same time, we introduced this embedding vector, basically what we call this basically affordance vector, which we can extract from videos, set of videos, and then apply to other images of the same objects, and we can guess where to rotate or where to hold. And we can learn these affordances all from this set of videos. And nice thing was once you extract this video vector, embedded basic affordance vector, we can directly apply to any new image without having to require, again, to have all these demonstration videos. So it's a pretty extracted. So once you get this knowledge of the affordance vectors, when you are given a new image of different view or different object, or different color or whatever, you can just directly apply this affordance vector to that image and get this heat map of where you think you should touch or where you should rotate or where you should hold, etc. Okay? And again, we collected a set of affordance videos from YouTube or from Amazon and all that. And then we apply our method to do this. So for example, when we watch this video on the left and we extract the affordance vector and we apply to the image on the right, you can see it's basically about grasping or holding this handle. And when you watch this coffee video, again, you can clearly see this video shows different viewpoints compared to this target image. And we predict this part is for rotation. Okay? And our architecture looks like this. I'm not going to go into details for this because it's not as important for now. But there are different demonstration videos, a set of demonstration videos, and then we have some encoder here, which looks a little more complicated than just box here. But then once we get this demonstration embedded vector, now all this video is useless anymore. So we have this embedded vectors, and we have target image. Then we have classifier, which one is about action classifier, and then the other one is about heat map decoder. So then you can predict basically where to pull, like this. Okay? The architecture is not as interesting, but it has some attention model in it. But I don't think we have to go into that here. But I just wanted to showcase what we can do from demonstration video to extract affordances from images. Or from videos, sorry. Okay? It's pretty high level, so I don't think there might not be many questions. But is there any question about this work? No? Okay. So I will move on then. For this work, I'm not going to go into any technical detail. I will just show some result. Okay, so it's about novel V synthesis. Another Taiwanese student here, Shawa, the guy who looks better than Tom Cruise, self-claimed. Okay. So here, mental rotation. So our goal was to, given some images of some basically on the left, our goal is to predict a new view of this same object. Okay. So we are seeing this side view, right? But our goal is to generate an image that's more like a top-down view, right? And then, so the way we did it, so motivation, so this work is very popular, I mean, this is a very classic problem, generating a new view from existing images, okay? But the trick we gave to this problem is to use multiple view images to generate this, this novel view, and also by accumulating information over time, okay? So suppose you are given one image, let's suppose this is the best you can do from this one single view, okay? But now you add a second view, this improve a little more. And then now you add a third view, it improve more, and et cetera, et cetera. And that was the basic idea, or the basic approach, high-level approach of this work, okay? And there's like architecture and so on. This is ECCV 2018, which is in next month actually going to be presented. But I don't think I will go into this. Just the high-level approach is just to keep adding more and more images to generate, more cleanly generate target image. So now you can see the third column is our result. And then the source is on the left. And let's suppose you only have single image. This is still comparable to other state-of-art method. When you have single source image, a single view, and you're trying to generate this target view on the second column, right? Our method is, I mean, arguably similar, or better or worse, but they're all similar to each other, right? But our model plays interesting things when we add more and more views. So as you see on the first, when you only have one single source image, it's a little blurry and so on. But as you add more and more views, it starts to be more crisp and cleaner result. Okay, you can see this from all these images too. And we also compare quantitatively, and obviously we say ours is best. And we also apply to different data too. And the same thing, okay? All right. So you can probably you can look at more results on our website, and also we have official paper release as well too. Okay. All right. So I'm probably not going to take any question for this one. I'm assuming. And now so this is about it for learning through observation for now, and the second part is about learning through interaction, which is a little more related to what I gave lectures about today, right? This is more related to reinforced learning directly, okay? So as I mentioned multiple times, humans learn through interactions, or also machines can learn with this indirect feedback, right? And I do multiple different research on this domain. And first one I want to talk about is multi-goal reinforced learning, okay? So what do I mean by multi-goal RL, reinforced learning here? So let's suppose we are trying to train a navigator, an agent to navigate the room, right? And let's suppose you are training an agent that can find or go to the balcony, okay? So how do you do it in reinforced learning? You don't have to look at this architecture. So how would you do this with a reinforced learning algorithm? You put an agent into the world environment, right? And you give a reward when he finds a balcony, right? That's as simple as that. And that's how we train an agent that can navigate to find a balcony or get to the balcony, right? So that's one way to train it. What if we want to train a robot that can go to the door? Same thing. We train an agent that can go to the door and then we give a reward when it gets to the door, right? So that's a simple reinforced learning. And again, do the same thing to go to shelf and etc. But the issue is, as you can see, there can be multiple goals for navigator, right? We might want to go to door, a balcony or door or shelf. And what if we have 10,000 different goals, or sometimes we even have, it's not actually even a discrete number of goals too, right? There can be many different objects or targets or new ones even coming up, which is not pre-trained, right? So it's really unideal. It's very unrealistic to train an agent for each different goal. You don't want to train an agent to go to balcony, and you don't want to train another agent to go to door. So you don't want to have like 10,000 different agents. That's very unpractical, right? So for this, our goal was to basically introduce a model that can have multi-goal input into the system. In other words, rather than just having state as an input to the agent, we also take the target as a part of input too, to the reinforced learning agent. So what this means is target, we specify where we want it to go. Okay, so target we can input like microwave, or we can put door or balcony as an input. Then this one model can be universal for any target we care about. Right? The intuition was many things when we try to find, and when we are training an agent to find things, it actually bypassed a lot of things we actually maybe initially didn't care, but maybe later will care. So during the exploration stage, it will observe everything we will. So we try to basically encode everything you observe in the world into some latent vector, so that it can actually encode all this knowledge about the surrounding world. So even when you change the target, even when the agent, the user actually specify new target, it can still get to that without having to train it again. Okay, so that's a tweak we gave to standard reinforced learning algorithm. All right. And with this, we train our agent. I showed this video earlier, but I don't think you guys understood what this was about exactly. So the goal was to basically train an agent, and in this case a robot, that can find our target, which is a microwave in this case. It actually goes to find a microwave. But we don't actually train it specifically for microwave. We actually don't even show microwave in the beginning. We don't actually train, during the training time, we never actually cared about microwave. But only during the test time, we specify the microwave, and it can actually find it. Okay? And same thing for door as well. It never was trained to find a door, but we was training as a whole universal goals with the different goals in mind, like a desk, table, sofa, and so on. And then during the test time, we actually give microwave image or door image, and it can successfully find all these target objects. Okay? So in other words, the motivation was to have multi-goal as input rather than as a basically encoded into the model itself. So you don't have to train it repetitively. Okay. Any question? Am I going too fast? Or too slow? Okay. All right. Oh boy. All right, so let's go. I will skip this one for now. I will come back to this in another slide, actually. I think it's better that way. All right. So another reinforced learning paper here. So the goal in this paper, this was iClear 2018. The goal in this paper was to train an agent that can generalize to different tasks or environment. Okay. So let's first talk about it first. Okay. So if you think about it, right, when you train, let's watch this. Sorry. So when you train an agent that can play a bowling, I think it's playing. It's a little slow. Oh yeah. So you see, let's suppose you have trained a reinforced learning agent that can play a bowling like this, right? That can hit 10 pins well, reliably, right? Then suppose you change the goal to hitting 5 pins. Maybe let's suppose the bowling was about hitting 5 pins, right? We have a reasonable guess that this agent should be able to learn to play 5-pin hitting game better than the agent that has never learned to play a bowling, right? So it's about generalization, right? And so the question was, how do we train an agent that can easily adapt to a different task or even different environment, right? So let's take a look at here. So we talked about this all day here, right? We have agent, and there's environment. We take action, and we get the reward. We keep repeating this, right? This was everything about today. So environment was always entangled into the task so far. But in this paper, we disentangled the environment task, okay? Because, for example, what does it mean? The environment is the same for bowling, right? The bowling game is the same game, but you just change the task from hitting 10 pins or 5 pins. Or in this room, let's suppose I learned in this physical world, let's suppose I learned how to open the door, but while learning it, I probably have to walk around it a little bit too. So I learned different kind of task, or I was trained, at least vaguely trained to do other tasks on the way while learning how to open the door. Okay, like maybe I learned to close the door, or I learned to walk, and different kind of actions. So that's why we are disentangling this environment task conceptually now here. Okay. So in other words, many tasks share the same environment. Okay. Like for example, tennis or squash are on the same physical rule, right? They both have this ball bouncing things. Or sometimes only the environment changes, for example, right? Playing tennis in a rain or on a sunny day, it's still changing the environment, but we have good doubt that actually probably someone who learned how to play tennis in a sunny day can probably play better than someone who never learned how to play tennis in the rainy. It's still in the rain, right? So this kind of a motivation or inspiration is how we tackle this problem. So now the question is, how do we generalize and how can we be more efficient? Okay. And the model we introduced here is like the following. So we have a given state, again, observation. And this is, again, the reinforced learning framework. So what we do is, rather than having one agent, one model that takes the input and goes all the way to action, what we essentially do is splitting the current state and the goal state. So it takes whatever current state is, we're disentangling also task information into the framework. So this pass function essentially give which action from one state to another. So let's suppose you are in the current state X, and your goal is to go to G. Then this pass function will generate how to get from X to G. And that's basically the goal of this pass function. And this goal state function is about what is the best next target goal state should be given current state, given this task. Okay? Let me reiterate it. Okay? The goal state function here. So this is a subfunction, right? This box is a function generating goal state or next target state given current under this task. So if I'm at this current state, if my goal is to open the door, what is the next desirable goal state? Is generating this is the goal of this goal of this goal function. Okay, and once you know where to go next, what is the next good target state, then we put into the pass function. So given the current state and then our next target state, we can generate action to do. So then it's naturally split it. So even when you change the task, this pass function itself stays the same, right? As long as you know where to go next, the pass function will just generate how to get there. So essentially the point was we trained this pass function, okay, which knows how to get from one state to another state universally. Then even when you change the task, you don't change this pass function as long as it's the same environment. Only thing that changes is the goal state function. What will be a good example? It's hard to give a specific concrete example here. Yes?
I'm not sure if my understanding is correct. So basically, we're given a task, and the goal state function is to generate a series of different goals. So let's with the
Solve goals,
path.
yes.
So with the path function, we can minimize the training between goals and goals.
Right, exactly.
Okay.
Yeah. So let me try to explain once again and why this is interesting. So essentially, no matter what task it is, the path function learns how to get from one state to another state. So given a state and another state, the path function will return how to get to, what is the best action to get to the goal state from the current state. And that's the role of this path function. And now if you think about it, this can be shared across any task as long as it's under the same environment. So which means that this is universal within the same environment. Right? When you change the task, it doesn't matter. As long as you know what state to go to from one state, this path function can generate a series of actions for you. So then why is that important? Why is that interesting? Then when you change a task from one state to another, only thing that changes is goal state function, because goal state function defines what is the other target state should be based on current task. If it's closing door or opening the door or moving, as long as it's the same physical world, this goal state will take care of the task and to tell me what is the next desirable state. And as long as by this goal state function generating next solve goal state, the path function can tell you how to get there. Okay? So basically one is about how to get there, and the other was where to get to. And where to get to is task specific, whereas this how to get there is environment specific. So there's one module is about environment specific model, one environment specific function, and the other one is a task specific function. And by splitting these two, by disentangling these two different functions, we can share them across different functions, across different tasks, or across different environments. So in other words, when you change a task, you only have to retrain this part while keeping this part, while we keep this part fixed. And when we change the environment, on the other hand, we can keep this part same, and as long as the task is the same, because next solve goal is the same. Whereas how to get there, we'll have to change in them depending on the environment, so we can change that too. Okay? Yes.
So the output of the path function is a sequence of action or just a single action?
Oh, so yeah, it's a single action, but you run again, then it will be just you will get next output. So basically, based on one single action, you take action, then the current state will change, and then once you get this new current state, then you can take another action and so on.
Okay, thank you.
Yeah. Yes.
So previously you gave the example of having a robot going from one place to another place within the same room.
Right.
That would be the path, that's like the path engine you have here. Is that the same thing?
Yes. Yeah. So yeah, if you have a robot in the same room navigating, yes, then the path function will be the same, because as long as you're in that location to that location or that to there, you have the same universal one. But the goal state will change depending on microwave or door and so on. Yeah.
Now in this case, do you have to train the two models together, or you can train them
Yeah, they are
separately?
jointly trained. So we iteratively train. So we first try to train path function a little bit, and then once we have some path function, we train this goal state function, and then we iterate it a little, and then until it converges.
But you also said that if you have a new task, you only have to retrain the goal state engine, so the model.
Right.
So you train that separately?
Yes. Yeah. In that case, we fix this path function, and we train this entire model again. So which means just training
So you
this
just
goal state.
converge faster,
Right.
basically.
It converges faster. Yes.
Okay, thank you.
Yeah. Thanks. Okay. All right. So the convergence now is what the question was about. So this green curve is our curve, and A3C or A3CL The point I want to make is that ours converge much quicker than any other standard method here. And this one, A3CL here, means it's a pre-trained network from other task, and you apply it to new task. So you just use the same A3C. A3C is just one algorithm. So we talked about A2C earlier today, and A3C is a more advanced version, most standard version. Okay, and then so A3C, the blue curve is the one you train from the scratch, and then the orange curve here is the curve you trained agent from other task, and you apply it to new task by fine tuning. So you can see it's a slightly faster than blue one, but then ours just surpass completely against others. And you can observe this from many other tasks as well. I'm showing this in one environment, one task, but in the paper we address in many different environments too. Okay. And I have a few more projects to go to, but let me first take a question here. Is there any question? All right. Okay, I can move on. So there are two more interaction-related projects I want to discuss, but I will come back to this after first talking about this topic, which is learning through question. Okay. Or learning over time together. So this work was about learning to ask questions. So what is the motivation here now? Okay. So how many of you heard of visual question answering? Okay, quite a few. So VQA is as simple as this. So when you're given an image, we as humans ask a machine a question. So for example, we ask a machine, when was this picture taken? And the machine is supposed to answer back to us, it was during the wedding. Okay? And again, we can ask the same question, a different kind of question to this image. So we ask, where is this picture taken? And the machine has to give us answer, this was during the London. Okay? So answering the question, human's question, was the goal of this project. I mean, this is the goal of this VQA challenge. And it's a very popular problem in computer vision. I don't know if it was already discussed in the previous lectures, but VQA is one of the most popular one at the current state, at the state of computer vision task, I think. But if you think about this task, there's a little bit of issue. So what if the machine doesn't know any answer? And then either he has to just randomly guess or say, I don't know, right? But how does humans work? So let's suppose, take a look at this. So it's what we call as VQA like a human, right? So suppose in this picture I ask you, or I ask humans, or machines even, what is the color of the food inside a pan, right? Right? You can answer. Many of you probably can answer this question already. But what if it's a 5-year-old baby, or maybe 3 years old even, and he or she doesn't know anything about pen, what the pen is? What will he or she do, you think? What is it? Yeah, probably the baby will ask me, what is the pen? Or where is the pen or whatever, right? That's the natural answer, rather than saying, I don't know. I mean, maybe the baby will say, I don't know either. But sometimes they will choose either, I don't know, or maybe what is the pen, right? Depending on their mood. So my niece, in this case, will probably ask, let's suppose, which is the pen. So I can then now tell you, or the baby, okay, the round one with a handle. So I can answer back to this. And then the niece now finally understand what the pen is, and she can say, it's yellow, right? So this is a more natural interaction, rather than just saying, I don't know, or randomly guessing it, right? So in the standard VQA framework, this is a very abstract version of it. So what happened is we have a question, including image, and we encode it, and we decode the answer, and we get the answer. This is a very standard technique, obviously very abstract version. But in our framework, or in our problem, we introduced this new problem of interactively answering question about the image, and that was our motivation. And for this, we introduced this model, which is using the memory network. I think Gonhi talked about it in the first day or something. But forget about all this thing. But essentially, the high-level motivation is we have an image, we encode a question, and once we have a question, essentially the machine goes to generate a query, which is a question the machine asks to us, and then it gets answer from the knowledge source, either from Wikipedia or from human and so on, and it encode response from human, and again it put into memory, so it accumulate memory over time by keep asking question to humans or knowledge source, and eventually when it feels like it knows the answer, it will generate the answer back to us. So basically, like in this case, who is under the umbrella? And again, let's suppose hypothetically the machine doesn't know what the umbrella is. Then it will ask us what is umbrella, and we give some response, and then it can eventually understand what the umbrella is and all this other information, and then we'll say to women. Okay. And essentially, we use VQA like human with some memory network here, and that was our motivation in this paper. But really, more goal was to have a more interactive system between human and a machine, so that it can actually naturally interact to answer questions from human. Okay. Is there any question about this work? Okay. All right. So for 20 minutes, let's see. Hopefully. So I will talk about a few more works until time runs out. So this work was about neural program synthesis from diverse demonstration videos. So again, it's a little related to interaction, but less than reinforced learning, but learning from demonstrations. Okay. So let's take a look at these videos. When humans look at these videos, we can abstract a lot of things and make recipe, or basically we can make order of how to cook food, right? And that's the skill the humans have. And in other words, we can summarize what's going on in these multiple videos into a common one program. Okay, so and that's basically what we call the recipe. In other words, is a program, right? Program for humans, right? We can look at the recipe and follow the order and make a food, right? It's a little more abstract than typical computer programs we write, but essentially it's one sort of a program, essentially. Again, so a program in our paper, the way we define it is a program is an interpretable and executable way to describe behaviors, right? Right, just like a recipe. So on the left, we have a demonstration of how to play games, and on the right, it's the program that generated these demonstrations. So usually we have this program, we can generate these demonstrations, right? But our goal now is get this program given these demonstrations, right? So how do we abstract, or how do we basically summarize behaviors in the demonstration into a single program? Was the motivation of this work. So basically that's what we call it, program synthesis from demonstration videos, okay? And again, interpretability is important for humans so that we can read this program and we can manipulate it or control it. We can change some parts if we feel like something is wrong, or if we want to add more functions, we can add it too. And executability is important for robots or agent. So so that we can eventually follow this program to execute some actions or certain demonstrations, okay? So again, what is a program synthesis? So program synthesis is essentially the idea. So the machines can write programs based on based on what we tell them to do. Okay, and then what we tell them to do can be in words, but it can be also in the form of videos, etc. So more specifically in our work, the way we specify the task is by this input and output pairs, right? So basically this initial state and the goal state, and we show this. And then we can generate a program like this. And this is a very well-known line of work. I mean, it's not yet as big, but it's starting to get some attention to it. So once you have this input and output pairs, we can synthesize this program output. But the issue in this sort of frame or this setup is that when we have a very complex programs, obviously just one input image and that one initial state image and a goal state image is not going to be sufficient to tell you how to generate all the programs, like a very complex programs. You need to see more than just the input and output, or the initial and ending states, right? So in this case, we used this demonstration sequence, basically set of a video frames, to synthesize this program. So we utilize a lot more frames than just a single input and output state or frames. Okay? So again, our problem formulation in this work is that we have a set of demo videos, like on the left. We have a lot of different demonstrations, and we train a network that can generate a program like this, a program that can describe the behaviors of the demonstration videos. Okay? So to solve this problem, we need to address a couple different challenges. So one is, how do we extract the unique behaviors in each video, right? So because if you think about it, a lot of demonstrations in cooking, for example, many things are similar. A lot of things are just all repetitive. You know, we just move arm, or we grab the handle. There are a lot of repetitive actions, but there must be something different or something unique from one video to another video. And that's basically where it creates a branch, like if statement. So if I grab this, or if something burned, I do something else. If something didn't burn, I didn't take a different action. So there's like a branching action, which means that this extracting unique points or unique behaviors from each video, or differentiating them is one of the challenge. And another challenge is, now we have all this difference, or we now extract all these diverse points in different videos. How do we summarize them into a single program is another challenge too. Okay? So for this, we introduced two different models. So the first one we call as a reviewer module. So because we review each video against the others to tell what are the unique components. And then we use a relation module from relation network. I don't know if anyone talked about relation network, but essentially we use a very popular relation network module to summarize all these differences from videos. Okay? So our architecture goes like this. The first component is about extracting unique behaviors again. So we have this reviewer module. So we have a lot of videos, right? Multiple demonstrations, and we encode into them. After encoding them, we have a reviewer module to extract the differences from different unique points about each demonstrations. So we have this demo features, which essentially encode what's different about them. And once we have them, we go through this relation module to generate this program vector. Okay? In other words, we summarize them into one single vector. Okay? And once we have program vector, we can just decode it to generate a program. Okay? So let's talk about this reviewer module a little bit. So reviewer module, again, is at a high level very simple. So we have a demonstration video, and we have CNN and LSTM architecture to encode into the demo 1 feature first. Okay? We have another demo, and again, we encode into the demo feature. So this encoder is a very standard video encoder. Okay? And we first extract all the frames using CNN, and then you use LSTM to encode it. So we summarize the video into this vector. Okay? And we have demo K, and we encode it to get this feature K. All right? And what do? Once we have this, we average them to get this overall tendency, what we believe it to be overall tendency vector. So which means it summarizes everything into one vector, entire behavior, all the video into one vector. Okay? But you can probably expect this to mush a lot of things into one vector. So a lot of good information is probably going to get lost in here. So now we have this average overall tendency vector. What we do is we review each video. Okay? We review demo 1 or demo 2 against this 10 overall behaviors. So we put this overall tendency vector here, and we have reviewer LSTM, basically reviewer model, to compare against So compare against each demo. So we have overall tendency, and we compare it against this demo, and we get the final demo feature 1. So now we can, the goal is so that this demo feature compare against the overall tendency. We extract what's unique about it. Okay, and we do this for each different demo So we compare each demo against this overall tendency vector, and then we extract the demo feature this way for everything. Okay, and that's basically the first part. So we have this reviewer model now, and then based on this, we extract all these unique behaviors. So once we have all these unique behaviors extracted essentially using reviewer model, we go to the relation model here, as I said. And the relation model is also, the motivation of this relation model is for each different demonstration, right? Demo 1 and demo 2, our goal, if they're different, we want to be able to create different type of branches, right? Which means depending on the condition, they're making different movements, and we want to be able to extract them out. And for this, we compare each demo pairs into infer branching condition, and that's where we use this relation network module. And we have demo pairs. We pair this up and extract some feature, and we compare another pairs, and we keep comparing all these possible pairs to get, and then using the relation model or network, we can summarize into this program vector now. So we compare all these differences and compare them, and then summarize them into one vector. Okay? And that's the motivation of this relation model. And once you summarize everything into this program vector, what we do at the end is just like simple decoding. Just this is like how you do it. So we have a program vector, and just like sentence generator, you just have a LSTM to keep generating different program actions items, action tokens. So define and running and move, if something, and so on. And that's what we do. And in the experiment, so, okay, first, is there any question about the model?
I have
Yes,
a very general question. So there should be exactly many to one mapping, because you have many demonstration videos, and it's necessary to only have a single program output. I think there might be like different ways of writing this program. Right?
You mean, is your question, so there are two different ways of interpreting. Let me ask you. So is your question about whether is there single program that can generate same output?
Yes, exactly.
No, and yeah, you're right. I mean, we can have different, at least semantically it can be different. Or I mean, okay, the other way. Semantically it can be the same, but actual program sequence in a language could be different, right? And then we evaluated that too. So how to evaluate that is actually itself a challenge. So if you have two different programs which behave the same, then how do we know it's actually the same program or not? And that's a program language question, right? It's a PL problem, actually. But yeah, so we try to attempt to evaluate a little bit from that angle. Yeah, you're right. It's not a unique solution, even if we overly constrain it. Yeah.
And another detail I want to ask is that for every demonstration videos, that you should only contain like single action. Like for example, like you're given a recipe, right? And there are multiple steps you should perform to finish a menu, right? Then is it necessary for every demonstration videos you only perform a single movement? Let's say?
Oh no, it's a long sequence video.
I see.
Is that your question?
I see.
Yeah.
I see. Because I mean, then it's a bit. I'm curious about like, is really the review module can really extract a certain portion of the video that's represent a certain.
So it's not
movement.
I think it's that's a good question. So the way to interpret the review model is not really extracting just a unique model, a unique components only, but really it's just that with respect to the overall tendency of all the general videos, what is a kind of different, or what is, how do you differentiate them from overall tendency? It was a sort of an interpretation. So because you know what kind of things people generally do based on this entire video, so now you want to extract a little more unique components of each demonstration, and that was a motivation in this case. Because if you average them out, a lot of things are just mushed into one, right?
Yes, because I mean, I can think of a very naive solution for this is that, okay, I try to do some kind of like segmentations on the demonstration videos that into for every video is into several segments somehow.
Right.
Video clips, and then I use, for example, something like a GPP,
Right.
determinant programming processor, to draw out the diverse and unique segments. Then
Right.
maybe I can follow the same like relation module and
Right.
do the same thing.
Yeah, that's, yeah.
Yeah.
But I think it's just, yeah, I guess it's a different approach in that case, yeah. Yeah. Okay. All right. So moving forward, I'll just show a few experiment results. I will go quickly now. So we evaluated our method on Carol environment and Wisdom. Carol is just one of the sort of toy environment set up for this type of task, and Wisdom is environment. It's based on a very popular game back in the time, Doom, which is called Doom, and people also try this type of problems on this too. And now we, yeah, there are a few baselines because our approach was ours was the first one to trying to solve this problem. There was no baselines to compare against, but we introduced a few different things. But I will skip this details for now. Yeah, I will just show the curve at this point. Maybe I will talk about this a little bit. So left is a ground truth program that generated demonstrations, okay? And then the middle is one of the baseline, which you don't know what the baseline is about, but there's a baseline method, which is a reasonable baseline, but generated this output, okay? But you can see in this generated output of the baseline, it doesn't get actually this branch, basically if condition here. It's just this turn right is correct. The turn right marker is correct, even though it looks different, because they are semantically the same behavior, right? It's just repeated twice of this, which is basically the same program here. But the problem is this if statement wasn't captured in this baseline method, and ours actually can generate this if statement correctly as well, and also this is semantically correct repetition here. And we have some way to evaluate this, and not completely, but we try to evaluate this as much as possible. And same for Wisdom. Again, this baseline basically got this if statement as a while. It got it wrong, essentially, whereas our method can actually get this program correctly, too. And yeah, we'll talk about this details of evaluations. But obviously, the point I want to make across is that our method can actually perform the best against other baselines, and especially in the Wisdom, the performance gap is pretty large, too. Okay. Yeah, we'll skip this. Yeah, I'll also not talk about this. Yeah. Yeah, so in conclusion, we introduced this new problem of learning to generate a program from the set of sequence input, like demonstrations, and we are hoping to extend it to different type of problem, more complex problems now too. And for this, we introduced the model that has reviewer and relation models into it. Okay, and our code and data set is available online now. My student wanted me to say this, so I'm saying it. Okay, and if you have any question, I can take it very briefly. Yes.
I see the experiment have a problem. The models cannot find a repeat in your demo experiment.
Oh, I see. The repeat. So okay.
Yeah,
I will.
in the yeah.
So here, repeat 2 of this turn right and put
Yeah, I
marker
think
is the same thing as
yeah.
this, right?
Yeah, but so they cannot realize the model cannot realize the repeat or
Right, because in the demonstration world, right, repeat or this is semantically same. So either answer is actually correct answer, right? And the goal is to get this a semantically correct one, rather than really getting this program sentence correctly. Because 1, it's pointless to get that, and 2, it's impossible to get it too, right? Because how do you know it was based on repeat or actual just writing twice? Even humans cannot tell, or right? Because they are semantically gonna produce the same from the demonstration perspective. Okay. All right. I have 2 more minutes. I will just talk about what the problem I'm solving here. Okay. So it's about assembly. And when you have a Lego, let's suppose our goal is to build this gigantic ship. How many of you can do this without any manual, if I just dump all the pieces to you? I think it's hard sometimes, even with the manual, okay? But anyway, so we know that humans use this manual to do this assembly, right? And it's not just this, not just Lego. For example, IKEA furniture. If you have IKEA furniture, you don't just look and then just assemble them. You actually look at the manual, and sometimes you make a mistake by putting different parts into different wrong locations, especially when you don't look at the manual. So our goal was to basically utilize this manual. Even for humans, you're using manual was the fact that we can actually use manual for many tasks for agent to solve the problems too. And I will not talk about this thing. There's a good motivation and all that, but we don't have time for that. So we tackled these 3 different problems to show this. So we use manual to solve these 3 different tasks. One is a tangram, right? And then the other one is stacking, boxes stacking. And last one is a furniture problem. So furniture is basically IKEA furniture in this case. So our goal, so suppose in this world, we have these pieces. And our goal is to build this goal state. So from these puzzles, how can we make this a shape? Or using these furniture pieces, how do we make this this a chair? How do we assemble it? And the instruction, basically the manual, tell you which piece to hold now, or which 2 parts to connect each other, right? Just like IKEA manual. And that's basically our manual per se. And we train a reinforcement learning algorithm, and this looks scary. Don't worry about it. So we train a network with attention component in it, and result is good. But now you can see, so this is solving tangrams. So the middle is current state. Okay, so I will show again. So middle one is a current state, or so. And the right one is a goal. So you can see that's attending where it should grab the boxes or the puzzles. So to keep moving around to get to the goal state, right? And I will skip this one, but it's the same for furniture too. So if you have no instruction, even if you train this reinforcement learning agent forever, it's like over weeks or whatever, it just doesn't even get any idea. You can see it's clearly not doing anything reasonable. But with ours now, there's a manual. So this is a current part, and there's a manual. And you can see it just keep moving around to attach to the right furniture, right? So on the bottom here, it connects everything correctly, right? So yeah, so that was basically this furniture assembly project. And there are more results also, again, online as well. And that's it for my time, I guess. Do you have any question? All right, so essentially today, basically I want to talk about how do we learn from visual information to basically learn to interact with physical world. And my ultimate goal is basically moving from vision from just what and where to how and why. And that's part of a motivation I want to drive it to you guys. Mostly in the first 2 lectures, I talk about reinforcement learning because that's one of the core techniques to train a network for interaction. But as I showed in the 3rd lecture, there are a lot of different problems you can also explore in the space of interaction. And that was my, I guess, key message I want to deliver today. So feel free to come over. I will be around for maybe 20 more minutes today. If you have any question, feel free to come over. All right, thank you. Have a nice day.